you see, what I want to talk about is atomism and relationalism. In a way, they enter in loop quantum gravity. But these two things enter with different aspects. So in particular, for relationalism, you see, one can consider the relational, take a relational view for the ontology of space-time. One can, I would argue that this is something that one is obliged to do in order to do quantum gravity, because of quantum mechanics, since we can take a relational interpretation of quantum mechanics, and because of general relativity, because general relativity obliges us to consider observables that are somehow always relational. This is the first point that I want to make, and the second point is about atomism. The fact that we wanted to do a quantum theory of gravity, so we needed to take seriously the lesson from quantum mechanics. I remember that there is this quantum discreteness that we have not to forget about. And so when we do quantum gravity, we need to extend the general relativity in a framework that is a discrete framework. Okay, this is the plan of the talk. So let's start with the ontology. So the ontology of space-time has been debated since the ancient times. I think that Nick is an expert of how these debates went back and forward between these two positions. So the first position is the one that says that has been introduced by the atomic school of Leucippus, Democritus. They introduced this powerful idea that there are some fundamental constituents in our world, and these are the atoms, and this moves randomly and crazily in what? In a vacuum, in a stage, and this stage is what we call space. So somehow this gives ontological meaning to the vacuum, to the nothing, but it gives gives to the space to live, to exist independently from the matter. On the other hand, this idea was opposed by people like, was really disliked, I would say, by people like Aristotle and Plato and all the Ateniense school, at the point that Plato never mentioned in his books the work by Democritus. Why? Because they thought that the only way to think about space was in relational terms, and so what gives space are just the relations between bodies. Okay, and this was the predominant way to see space till the 17th century, when this debate started again. So on one side you had the relational point of view defended by Descartes and Leibniz, and on the other side Newton. So Newton, with this new idea, reintroducing somehow the idea that space can have his own right to exist independently from matter. And okay, so the predominant position passed from this side on the other side because of the effectiveness of Newtonian mechanics. So nowadays it's legitimate to ask, can we reconcile these two positions? Is that a way to put together these two positions and go beyond this kind of duality? So in order to do this, we need an intermediate step. And this is has been given by Faraday and Maxwell when they introduced the idea of field. So you see the ontology here of the world split now in two, the things that actually exist, the matters. So you don't have only particle anymore, but also these fields. So then a new step came with special relativity, putting together space and time, and entangling them into a unique object. But in the same period, the new revolution brought another convergence. So this split was reconciled in this in the notion of quantum fields, where particles are just some excitation of the fields. So the next step came with general relativity, putting fields and space-time together, and coming out with the idea that space is just a field like the others, and this is really the core of what we call background independence. Space-time is a dynamical object, is a field like the others, like the other matter fields that we know. So the next step should be the one made by quantum gravity. It's to reconcile the quantum vision of fields with this vision of covariance fields from general relativity, and one would be tempted to say that everything that exists in the world is just a manifestation of general covariant quantum fields. This is some kind of unique thing that exists in the world. So I wanted to try to convince you about this convergence, ontological convergence, and show you how this is achieved in loop quantum gravity. So the core are, as you can infer from the title of my talk, are the atomistic point of view and the relational point of view together. And let me first comment about atomism. Atomism here is meant in the broadest sense. I wanted to connect, I don't want to say just discreteness, because I wanted to connect somehow with a long tradition of discussion about and connect also with the discussion about change, since the notion of discreteness in the ancient Greek debate was related with the notion of change. So change and discreteness goes together, as opposed to a Parmenid world that doesn't change and doesn't have and a world that in which you can chop your space as much as you want down to infinity. So this is important. This debate is not trivial for what we want to do, because it becomes important in quantum gravity. If you think that there is some fundamental discreteness down there, then you will not do quantum field theory in the same way. You don't want to take your renormalization group down to infinity, to an infinitely small dimension, because there is this natural cutoff given by the quantum nature of space-time. So, okay, this seems an obvious statement, the fact that quantum mechanics imply discreteness, but it seems that it's not taken so seriously by all the people who work in quantum gravity. You know, quantum gravity is there is a quest for quantum gravity. There are different approaches, but only few of them take this idea seriously. I would say loop quantum gravity is probably the approach that takes this thing more seriously. In string theory, you have the same thing. You have the fact that you cannot go below the Planck scale, but and there are the causal set approach takes the same attitude, but is not so spread by and not so. There is no consensus about this. So my first
Francesca,
point, yeah.
By discreteness, do you also mean to include a minimal length scale, but not actually discrete space-time?
How can you?
I'm just trying to understand the different senses in which these different proposals that you mentioned are both fall under this category of discreteness.
I think so. I think that once you think that there is a minimal scale, you cannot avoid to think about some discrete space-time. Even though it's important to have clear in mind that when we work in loop quantum gravity, there are two kinds of discreteness there. One is the one that is a genuine quantum discreteness that comes from the fact that all geometrical quantities are quantized with the discrete spectrum, and this is a true physical discreteness. There is also another discreteness that comes from the fact that we use a graph in order as a tool for our theory. But this kind of discreteness is it's not a physical one. It comes from the kind of interpolation that we want to do. It's like the lattice in QCD, for instance. I would put them on a different level, let's say. Does this answer your question?
A little bit, but maybe we can talk about it more during the questions at the end.
I would like to point out that the T-duality in string theory is an example where there's a fundamental length scale that still continues.
That's what I had in mind.
Yeah, it's an example where you can't go below a certain length.
I would like to ask you a question because I know string theory very badly, just what I learned at school. So, come on, in all university they teach string theory nowadays. So, I mean, if you take your string and you go to an energy that is higher than the Planck energy, then your strings, your closed string open up, right? So in a certain sense, you cannot go to energies that are below that scale. Is it right?
I think it would require a longer discussion.
Okay, let's keep this for later then. So what I want to say here is just the fact that to focus on the quantum nature of every field theory, and the fact that you can define your quantum field theory by considering some Hilbert space, some algebra operators, and some transition amplitude that is determined by the Feynman rules of your theory. And we will see that we are the same in quantum gravity. And and this was the comment that we were to which we were already arrived before. The fact that there is a minimal length, and this is an argument that goes back to the history, really to the history of quantum gravity. This is a very simple argument to which I think you are all familiar. But let me just briefly sketch it. It's just the fact that if you wanted to investigate some very small region, you need a momentum, a high momentum. Because of special relativity, high momentum means high energy. But since we know from general relativity that all energy gravitates, this means that you have a mass, and this mass. The smallest is the region that you wanted to investigate. The more this mass is large, at the point that this match can form its own Schwarzschild radius, a black hole horizon. So this gives a limit to the kind of region that we can investigate. We cannot go below a certain radius of this black hole. And if we put these equations together, what we get is a length that is the notorious Planck length. And this was realized in 1933 by this guy, Matej Bronstein. You see, it was him to realize that if we wanted to do a quantum theory of gravity, we have to do a revision of the classical notion of the short distance domain, of what happens at short distance. Okay, this is everything that I wanted to say about atomism. About relationalism, let me start from, I have two different comments, one about quantum mechanics and the other one about general relativity. The one about quantum mechanics is this. It's the fact that all the time that we consider some quantum mechanical events, every time that we want to do an observation in quantum mechanics, we are always dealing with two systems. I encourage you to think about this and try to figure out an example in which this is not true. I claim that this is always true, and this has been recognized also. I mean, if you take a different interpretation of quantum mechanics, they all share these things somehow. In the Copenhagen interpretation, you always need a measurement apparatus. If you take another very popular interpretation like the many-word one, all the time that you have, every time that you measure a certain value, this value is always related to the particular branch in which you are. So this relationalism seems to be really at the base of quantum mechanics, and the relational interpretation of quantum mechanics is nothing but the realization of this relational nature. So in this interpretation you take very seriously the fact that we always talk about relational variables, and we keep in mind the fact that distinct observers may give different accounts of the same sequence of events.
What are events?
Events, it's everything, every interaction in nature. So it could be the experiment that I do with my apparatus while proving the spin of a particle in my lab, or can be a scattering between photons in the interstellar medium, or can be even it can be even some interactions between two quanta of spacetime. So it could be even the geometry itself that interacts.
But you're assuming the interactions take place at some time, something of that sort, because an interaction for me is eternally Hamiltonian.
For me,
it's always taking place.
For me, interactions, interactions is something that this will become clear in a couple of slides. But interactions are you're right, are something that happens at a certain time, and they can be seen as the boundary of some process that is four-dimensional, so that knows about time, but without preferring any special time.
So you're imagining like little sparks in the world.
I think that there is no meaning. Yes, I think that there is no meaning of talking about time, if but as a sequence of these interactions.
But these things are not part of standard quantum theory. I think you have to be more precise. I mean, I don't see any of those things.
Oh, you see only these things?
No, but I'm talking in the theory. In the theory, where is that in the theory?
Yeah, you will see it in a couple of slides.
Okay.
Yeah. Are there other questions? Okay. Okay, before going to the slides in which this will be clear, I wanted to comment on the relational nature of general relativity, about which we have already heard a lot this morning, because actually the talk by Bianca addressed this question when she was speaking about the introduction of dust matter in order to, as a reference in order to do general relativity. This was actually an idea introduced by Carlo Rovelli in 1990, and from which Kukesh moved, and you have seen there is a lot of work about this. And the realization here is the fact that when we talk about observables in general relativity, these observables are always relational observables. They are the so-called partial observables that are defined in the work by Carlo Rovelli of 2002. And the idea is that every time you want to make a measure in general relativity, again you are always obliged to make this measure with respect to something else. So, for instance, here there is an example. Every time you want to measure something, you have to fix your coordinates. This fixing of the coordinates is this something else that you have to add to your description in order to give meaning of your theory. So there is this relational core in general relativity, and this takes me also to a notion that has been discussed in the previous talk, that is the one of contiguity. So everything makes sense, all these interactions, all this description of interactions makes sense only when we can say that things are one next to the other. This is the way we can describe things in general relativity, and a more general, a regional spacetime can be seen exactly as a patchwork of all these processes that are defined by this notion of continuity. This is a way to phrase the issue of locality, an issue that entangles together. So the relational aspect of general relativity and quantum mechanics can be seen as in terms of the issue of locality, in the sense that again all the time that the basic idea is that everything that we can discuss are local interactions, and so we can put together, we can make a map between what are the processes in quantum mechanics that becomes some, in general relativity, the process would be just a space-time region, and what is a state? A state would be at the boundary of this space-time region.
So, Francesca,
yeah.
Does that mean that we can't discuss EPR, non-local EPR correlation?
No, it's the opposite. I mean, well, this doesn't have to do with quantum gravity. It's more generally a problem in quantum mechanics. But there has been some nice works in the past years about the EPR paradox in the context of relational quantum mechanics, and the claim is that this paradox is solved because exactly because when it makes sense to talk about what are the state of the system that you are describing only when an event has already happened, when you have already proved you have already seen some interaction. So you would not make claims about what is the state of your system before making such a measurement. So the idea is that this is the core, I think, of the relational interpretation of.
I didn't mean to derail you. We can keep it for later if you want to go on. But
I don't. Well, the point is that when I was saying that in relational quantum mechanics, one realized that different observers would give different accounts of the same sequence of events, is exactly related to this, in the sense that suppose you are making some experiment in your lab and you measure a spin up. So before you had a state in which you have a superposition of spin up and spin down. So you make your measurement and you have the results spin up. But then if another observer that doesn't know about you, he would see you entangled with the system that you are on which you are doing the measure. So for this external observer, the quantum system is not the spin up and spin down particle, but it's you to get it. It would be a state about you and about the particle together. So because of this, would not make sense for this external observer to say that the particle is already in a state or the other.
So there's no locality.
There is no locality. Yeah, and all the interactions are always local somehow. No, of course, the states knows they are entangled one another, but they need to have this contiguity. They should the state is exactly. So coming back to the discussion that we had before, what is a state? A state is a bookkeeping for all the interactions that happened before. So because of this. There is entanglement, but there is entanglement with there is notion about there is knowledge about other systems, but only systems that has interacted before. I want to go ahead, but well, actually, I wanted to answer. Here is the answer to the question that Daniel was making before. The fact that. So what we get, the picture that we get now is that if we take a chunk of space-time, and this answer also to a question that was done before, this is probably the difference between the techniques that are used in string theory and the techniques that we use in loop quantum gravity, because working in general relativity, people have realized that it's much more effective to not to work with asymptotics, but to work on finite regions. So if I take a finite region of space-time, a four-dimensional region, so this fixes some boundaries, and the states lives on this boundary. So this region is four-dimensional. But and it's a Lorentzian region. It's some Lorentzian space-time. But here on the boundary, I have some space slice where the states are my theory. So does this answer to your question, Daniel? No.
No, because you keep saying things happen, and these interactions happen. I have the feeling of what is an interaction happen. I just don't see these things in the theory.
When do you agree that if I compute the scattering of two?
You project. That's when you project, because you have measured a particular property of the final state. Then you project. How many particles do I obtain if I scatter a photon with them? Well, you project and then you compute. But that involves this projection and this measuring and this basically Copenhagen interpretation. What you want is something that does not involve that, and things happening irrespective of people measuring.
I want things to happen even without the Copenhagen interpretation.
That's why I don't see that in the theory.
Well, let me think more. I think I will think a way to phrase better the thing in order to make it understandable. Okay. Okay. Suppose you have followed me and you agree with me that you need to take this chunk of space-time on which you want to prove your theory. So the theory will be defined, as I was saying before, for a general quantum field theory, will be defined by some Hilbert space, by some observable algebra, and some some transition amplitude. And these are mathematically well defined in loop quantum gravity. So in fact, they are so well defined that I can just put them on a t-shirt. And this is the definitions. Okay. So my claim is that if you take this t-shirt, then you can
There's something very bad about that t-shirt. The verb to say is conjugated in the past. Why you do that?
Because there is not, or because you think that there is no time. It's just for historic.
Because you need that to have happened before space-time.
Well, we should talk about causality and causal relations. We haven't arrived yet to this. Okay, so taking everything together, I wanted to say that we can put together the atomistic point of view, the relationalist point of view. We can put everything together in some notion of space-time that is at the same time substantivalist and relationalist, and this is achieved in loop quantum gravity. So loop quantum gravity in a slide would be a theory about quanta of space-time. Each of these quanta is locally Lorentz invariant. Actually, I would say that because we have been talking about emergence, so my point of view about my perspective on the theory is that we assume the fact that there is a four-dimensional. We see some four-dimensional space-time, and we see Lorentz invariance in the world. So you start from this, you take seriously the Lorentz group, and you construct on the Lorentz group. So because we said we wanted to use a boundary formalism, we wanted to study just a finite region of four-dimensional Lorentz space-time. Here, this defines some boundary, and this boundary, on this boundary, we are left only with the rotational part of the Lorentz group. The rotational part of the Lorentz group is just SU2. And this SU2, the SU2 elements, algebra elements, will become exactly the variables of loop quantum gravity. So in one slide, the states of the theory that lives on these boundary states, on the boundary of the four-dimensional region, are states that are defined how? They are labeled by these three things. So the first thing gives how much is big each quanta of space-time. The second tells you about how much each quanta interacts with its neighbors. This is an area. And then there is the graph, and the use of the graph is just a way to code the adjacency relations between all these quanta of space-time. This quanta of space, actually, because we are on the boundary. Then, another question that arises before is how do we see that there is a geometry there? So this picture is very abstract, and I have defined only some group variables, but if I add this condition, so I take these vectors that are actually nothing but the generators of SU2. And I have the constraint that a certain set of vectors closed give, if I sum them, I obtain 0. This condition automatically defined a metric. This is a theorem from Penrose of the 70s. So, I mean, from the 70s we know that we don't need a manifold to define a notion of distance. We need just this set of vectors and a closure constraint, a Gauss constraint. So, I think because of this atomistic perspective, it's very nice that we start from these group variables, we quantize them, and the corresponding operators give us some operators that corresponds to geometrical quantities. And these geometrical quantities are the area, the volume, the angles. These are things that we can measure, we can observe, and they have a discrete spectrum. So here it is a concrete realization of the presence of quantum discreteness in this theory. To conclude the picture, this short description of loop quantum gravity, I have described the kinematics. What about the dynamics? Well, the dynamics is this sum over all histories, all possible histories of this space quanta. So I say that I describe the state with some graph, and I see how these relations between quanta evolves into another state. So this is given I can compute transition amplitudes between one state and another state of the geometry, and this transition amplitude is defined satisfying some properties such as the superposition principle. Locality. There is a notion of locality here that is the fact that the full transition amplitude is given by the product of single vertex amplitudes. Okay? This is the notion of locality that we have in the standard quantum field theory. There is the amplitude is fully Lorentz covariant, and finally one can study the semi-classical limit of this amplitude. And there is a beautiful work by John Barrett and collaborators dated 2009, in which they have shown that this transition amplitude actually in the semi-classical limit gives back general relativity. And as David was saying before, there is one can try to prove to do the calculation in some kind of simplified situation, such as the one of cosmology. So I take some loop quantum gravity states that describe a homogeneous and isotropic geometry. And I compute this transition amplitude, and so there was this. I compute this transition amplitude, and what I see is that I can check where this transition amplitude is peaked, and we discovered that it was peaked exactly on the classical solutions, such as the Friedman-Robertson-Walker one, the Friedman one, but also for more complicated cases, such as the de Sitter space with the cosmological constant, or in the case of Bianchi 1, this has been proved, and it's very encouraging that we can get back the correct classical geometry. So, as I want to make a comment here, because Daniele was mentioning this research program is in fact for the first time an attempt to make quantum cosmology with the full theory. We are not just quantizing a single degrees of freedom in order to do cosmology. Well, we take all the technologies, all the tools from a tentative full quantum gravity theory, and from this we do cosmology. Okay? So, yeah. So, to conclude, perfect. To conclude, what does exist? Does space exist or emerges from relations between bodies? Well, I hope that you go back home and and think about the possibilities that we have to merge these questions into a unique question, that is how to think an ontology in which existing and being in relations, interact, are exactly the same thing. There is no other way to think about existing but interacting. This is concretely realized. This is the picture that we should have in mind when we do quantum gravity. We have to take seriously the atomic point of view and the relational point of view while doing quantum gravity, because these are the lessons from quantum mechanics and from general relativity, the lessons that we want to import from our old theory in order to construct our new theory. Space-time is a process, and this is completely realized in quantum gravity. Thank you for your attention.
5 minutes before lunch to take a few questions. Go on, Chris.
Okay, I have sort of a smaller point which is connected to a bigger question I have. You've identified quantum with discreteness, even as the title of one of your slides. And I would beg to disagree with that, because I don't think that discreteness is neither necessary nor sufficient to really get at the heart what quantum theory is about. It's clearly not sufficient because we have causal set theory, which is a discrete theory, which is not quantum. That's the easy direction. It's probably not necessary because even in quantum theories, even though it's true that some things are discrete in some precise sense of the term, not everything is discrete, and there's nothing necessary about something space. Temporal.
Okay, my education comes from...
Francesca?
Yeah.
So everybody, I'm going to try and get a few questions in so we keep them as quick as possible.
Okay.
So that's just a smaller point.
Well, you don't get to go again then.
Okay, I answer. When you do, my education is in quantum field theories, standard models, and so on. When I study the standard models, when I study QCD, when I study all the other fundamental interactions, it's always about some symmetry group, some connection that is associated to this group, some particles that is associated with this connection that transmit the interactions. So, in my mind, I want to do quantum gravity in this way because it's a successful way. So now, okay, you tell me you don't have to have this kind of, you don't need quanta to do quantum gravity. Very well, but first I would like to ask you, please do QCD and do QAD without the quanta of the fields. So,
Brian.
I probably this should have been clearer to me, but you said that something important comes, the discreteness, I believe, comes from the Lorentz symmetry.
Yeah.
That was local Lorentz symmetry related to the tetrad.
Yes.
Possibly you could simply gauge fix that. So I'm surprised that anything interesting would follow quantum mechanically.
So what is your? So your question is that you can gauge fix. Well, in a certain sense, you can see the fact that you are choose a given boundary as a gauge fixing. You are choosing the kind of lapse on which then you want to integrate. So, but then nevertheless, this is a gauge fix that leaves you with the rotational part of the Lorentz group, and this is actually the kind of symmetry that is the base for the definition of the states and for the basic variables of the theory.
So, is it possible to implement a gauge fixing in the formalism and still have interesting features up here just for a different reason? Or
I think so. I think that there are about gauge fixing that there are some very interesting recent works. In particular, I would suggest you to take a look to the last paper of Alessi, Ciafrani, and Rovelli about this.
topic.
It's an interesting research topic.
So I just want to sound a note of skepticism about the use of relational quantum mechanics in this context. And I appreciate that we need some sort of solution to the measurement problem ultimately if we're going to take this theory seriously, ontologically speaking. But my feeling is that a theory in which, an interpretation of quantum mechanics in which events don't have definite outcomes in the sense that each observer might experience a different outcome to some particular measurement in a sense. So the sense is that I measure spin up, you have this description of me in a superposition of measuring spin up and spin down, and then you might measure both of us and find spin up. There's nothing inconsistent about it.
In the moment in which you and me get together, we will see that our results will match. But
so
the point when you discuss the EPR paradox and so on is the fact that the two observer, me and you, are not yet in contact.
Understood.
Yeah.
So, well, my worry is this, that you either end up with some sort of Everettian interpretation in which every outcome is realised, or you end up with some sort of solipsism where you're kind of on your own interacting with these sort of images of other people, but it's not clear what's going on. And applying that to space-time, it seems that solipsism is a very real worry in that you're sort of measuring definite outcomes of spatio-temporal variables, and you're collecting those as you go through life. But everyone else has got their own path through space-time, their own space-time.
Very well. So, if I have to choose if to worry about going in an Everett direction or in a solipsistic direction, probably I will go for the second, in the sense that not for Everett, but because if you look at the original papers, there are all the things that are then taken by the people who are working in many words, in the many words interpretation. But I think that here the point is that there is no reference to the collapse of the wave function. In this picture, you don't give ontological meaning to the wave function, in the sense that, one way to realize this, a good practice would be always, when you do quantum mechanics, would be to go back to the original classical theory and to see what kind of object corresponds in the classical theory to your quantum object. So for the wave function, the corresponding object is the Hamilton function. So I would ask to all the people that works thinking that the main point in quantum mechanics is the wave function and its collapse, if they think that in the classical world is made by the Hamilton functions. So my answer would be no. So let's go back. So the other option is to be solipsistic. Yes, okay. I think that this is something that philosophers should help us to discuss. Yeah.
I actually think it's a false dynamics.
You want to last question?
Sure. I'm worried that the way you use relationalism here is a little bit detached from the grounding in the historical debate. That in the following sense that I think is relevant for your argument. That normally people think about relationalism as a stance about the metaphysics of space and time, but here you really talked about relationalism of observables. And back in the day, this was called relativity, right? This is the namesake of the theory, but it's not clear how that aspect is really connected with the old relationalism debate about space and time. And on account of that, it's not totally clear how relationalism as such can really be a guiding principle for quantum gravity if it's really the relativity that's a guiding principle. But on the other hand, I think that everyone is going to agree that relativity, in a sense from the theory of relativity, should be a guiding principle. So in what sense is there something really, a new novel principle that we should be adhering to that people would actually disagree about?
Well, I think that if it was so obvious, we wouldn't have all the talks by Bianca, for instance, about all this notion of partial observables and so on. So, I mean, it's not that everybody is focusing in his or her research directions on this aspect of the theory. So what I would have liked to do with this title, with this talk, was to encourage people to go to look in that directions, let's say. Then if this is related or not with the historical debates about relationalism, well, I would say that this is I would like to see a path through history, and this is, I would claim that this should be our way to think about relationalism now.
Okay, let's just say thank you one more.